So, hello everyone. Thanks for joining us for this NL seminar. Our guest speaker today is Qinyuan Ye. Sorry, 1 second. So Qinyuan Ye is a fourth-year PhD in computer science at the University of Southern California, advised by Professor Qinyuan. Her research interests lie in natural language processing. In particular, she is interested in approaches that reduce human annotation efforts, including methods leveraging distant supervision, high-level human supervision, for example, explanations and instructions, and meta-learning. Prior to USC, she was an undergraduate student at Qinyuan University, majoring in automation. And today she will be talking about acquiring and understanding cross-task generalization with diverse NLP tasks. Please join me in welcoming Qinyuan, and I hope you enjoyed the talk.
Thank you, everyone, and hi to everyone also. I'm Qinyuan. I'm so glad to be here today to present my work on acquiring and understanding cross-task generalization with diverse NLP tasks. And these are works that I did with my wonderful co-authors, Bill, Jen, and my advisor, Xiang. So let's get started. Some motivation of my work is this is how we train a machine learning model to a new natural language processing task. We typically download a pre-trained model and fine-tune them on some human annotated data. And this general recipe has helped us build many successful NLP applications. So yeah, pretty good. We have solved like a lot of problems. But we're not done yet. There's still much room to improve this recipe. So my work has been focusing on how to improve the supervision signals and how to learn more efficiently like human. So one problem with these human annotated data is that models need a lot of them to actually learn that task. So the models are very data hungry. And as a result, it will be very expensive to collect the data and train a model. So this slide is trying to summarize how machines learn a new task, an NLP task. But as humans, we gather supervision from different sources in different ways. So here I'm trying to recollect how I learned a new skill or a new task when I was a child. We learn from understanding instructions from our teachers or senior people, and we also learn from explanations and feedback we get from others. And also, some people, they are very versatile. They can do many things. They have many skills and they adapt quickly to a new task. And also some people, they can decompose and recompose some skills from their past learning experience. So these are things that partly inspire some of my work. And in this presentation, I'm going to focus on these two parts, like how to build a model, NLP model that is versatile, and maybe we can train it to decompose and recompose skills. And before I introduce my work and projects in more detail, I want to highlight a paradigm shift or a concept shift that I'm going to constantly bring up in my presentation. So what we've seen before commonly is, I would like to refer to it as instance level learning. Basically, you are given a task and you have a train set, development set, and test set, and you want to generalize from a few training examples to the unseen test examples. But what I want to explore more in my work is what I refer to as task level learning, where you have so many tasks and you have a set of train tasks that you've seen before, and we are going to test your capability on a set of unseen tasks. So we generalize from a few seen training tasks to multiple unseen test tasks. And what we've seen in instance level training becomes just a task data point in this task level learning. So like in high level, in task level learning, a task is your data point instead of a input output instance is your data point. And this is also sometimes I refer to this capability as task level generalization or cross-task generalization as specified in title. So this is the core problem or capability that we want to explore and teach the models to have. So yeah, that's pretty much for the introduction and background. So the first part of my talk will be this piece of work called CrossFit, a few-shot learning challenge for cross-task generalization in NLP. This was accepted to EMNLP last year, and a short summary of it is that we collect 160 diverse tasks in NLP. Like we gathered these from the community efforts. They open source their data, and we try to build a few-shot learner that can generalize across these diverse tasks. In fact, this is not a completely new concept. This is closely related to the concept of meta-learning or learning to learn in some previous literature. So in this slide, I'm trying to present some work in the computer vision community or robotics community. There are already efforts that trying to build great learners from diverse tasks. So here are a collection of computer vision tasks. And on the right-hand side is a collection of robotics tasks that use handle to grab things, to unlock a door or something. But what we're discussing here is natural language processing tasks. And this topic is relatively underexplored for now. Some relevant topics include intermediate task transfer in NLP, where you first train a source task and then train a model, keep all the weights and train your model on the target task. People have find this to be very useful, but they mostly focus on one-to-one transfer. Like you have a one source task, one target task. And what our project is special in that we are interested in having multiple source tasks and also multiple target tasks. And also there are some efforts of meta-learning in NLP. Here are two examples of doing few-shot relation classification or few-shot learning with diverse classification tasks, but like the scope is limited to classification tasks. So either the tasks are synthetic or the distribution is a little bit narrow. So we want to build on top of these and have a diverse distribution of NLP task formats and goals to stimulate a more realistic learning environment. And also, we are very relevant to few-shot fine-tuning. You're probably familiar with these terms of prompt learning or template-based learning. I would say they are relevant, but they are still more focused on instance level generalization, how to learn from a few examples to and generalize to more input-output instances. But in this work, we want something called better cross-task generalization. We have a set of trained tasks marked in green here and test it on a set of different tasks. So that's how we separate from this prior work. So yeah, that's pretty much about the background and prior work and how we want to make our CrossFit paper more unique. So our problem setting is we first need to define task. I've been talking about task level generalization for a while now, but in fact, it's very hard to define what a task is. The meaning of the task is very overloaded. It can be categorized at different granularity. You can say classification versus QA are two different tasks. You can say binary QA versus reading comprehension are different tasks. You can also say QA in science domain and in news domain, they are different tasks. So we take a shortcut by having a very general formulation. We define a task with its training and testing examples. So a task is a tuple of a train set, a development set, and a test set. And more on defining task, we are interested in cross-task generalization. So we need to have a collection of tasks and partition them into something you've seen and something you haven't seen. So continuing on the last slide, basically what we are trying to build is something that looks like this. You have three partition or like three sets of tasks, train tasks, dev tasks, and test tasks. And in each task, there's a train set, dev set, and test set. So there's this two-level thing happening right now. And I hope this figure explains well about what our data looks like.
Yes. So you said there's a train, dev, and test for every task, whether it's seen or unseen.
Yes.
And then so what I see here is a train, dev, and test for tests 1 through 3, right?
Yeah.
And then only train for tests 4 through 6. Is that the idea?
Oh, sorry. I should use different numbers for these. They are different tasks. Like
So dev tests are also unseen relative.
yeah, there should be 7, 8, 9.
7, 8, 9, and
Yeah,
10.
that was kind of my question.
Oh, I see. And then within task 1, there's train, dev, test. And
Yes.
within task 7, there's train, dev, test.
Yes.
Got it. Okay. So 1 to 1, 2, 3. You should take this as rename.
Yeah, I should rename it. Any other questions? Let's get going. So this is how we define task in our data. And we also define the problem setting by defining the learning stages or how your model should access the data at different stages. So this figure shows the prevalent pipeline of having a pre-trained model and then having downstream fine-tuning to your final model. And in our setting, we add this additional stage called upstream learning. You can apply any kind of algorithm there, but the goal is to let it learn from the set of seen tasks and so it reaches another set of weights that is probably closer to your final model. So it might help you learn more easily. So yeah, pre-trained model, apply upstream learning, and then fine-tune on unseen tasks. This is what we do in our setting. And we also need to define evaluation metric. How do we define this as successful? So we define this thing called average relative gain to measure the overall performance gain on all the unseen tasks. So here is an example. Let's say task A and task B are unseen to you. And if you adopt the prevalent pipeline, you get a performance metric. You use the right-hand side pipeline, you get another performance metric. Let's say you get, after the upstream learning, you improve from 50% to 70% on task A. That gives you a relative gain of 40%. And you do the same math for task B, and you compute their average. So in the end, you get this number of 7.5%. But I have to say this is not a perfect metric. It helps us to understand model performance in a general way, but we still will plot out these numbers for better understanding. In fact, when we compute this relative gain, we see some like really small numbers as the denominator, so we kind of explode. This is the case we want to avoid, but it actually happens. So I would say take it as a reference, but also look at the full picture. And yeah, the problem setting is probably a little complicated we have one more slide to introduce it, which is the task partitions and data we use. So to help us do experiment in the setting, we collect 160 diverse NLP tasks from public sources. So there's a very useful tool called Hugging Face datasets that hosts a lot of the public datasets with a unified and easy to use API. And we convert these data into a unified text-to-text format for our models to learn more easily. And arbitrarily, we decide to have 16 examples per class for classification task and 32 examples for other tasks. This is borrowed from other Few-shot learning literature. And we release code to help other people to get the exact same data instances as we get, so we can compare. And we manually create a task categorization and sub-categorizations. We basically categorize the task into 4 major categories, like classification, QA, conditional generation, and others. And within each of them, there are subcategories. There are more details in the paper, so if you're interested, please take a look.
Is this all in English?
Oh yeah, we did use like whether task is in English as a selection criteria, but that's definitely a limitation.
And that means there's no translation.
There's one like sign language translation thing.
Oh, so is that multimodal?
Oh, I'm sorry?
It's multimodal then?
No, it's like it's just sign language has different like parsing or segments.
With the name of the sign.
Yeah.
Okay, cool. And you said that they're in a text-to-text format. Does that mean when you're doing classification, you're still treating it as a generation task, so you can generate something that is not in the class space?
Yes. Yeah, that's just to ensure we can put them together.
And even the question answering is not span bound.
It's not span like the model can generate anything, but
I'm trying to also see what you said for regression. Yelp review, full motion recognition. Okay, but you're still looking for some text that comes out at the end. I see. Okay, cool.
yes. And adding one more layer of complexity to it, we have 160 tasks. We want to test whether you can train a model that learn on a set of tasks and perform well on another set of tasks. So we define these different partitions to test these capabilities. So one of our first partition is random partition. They are randomly split into 120, 20, and 20 for trained dev test. And there are some other partitions that we designed for controlled analysis. Like we do non-classification task to classification task transfer, and like non-NLI task to NLI task, or non-machine reading comprehension to machine reading comprehension task. It just helps us to understand the capabilities, or like, I mean, the first one definitely looks very challenging, but the other 3 perhaps are easier, but we'll see with our experiment results.
I would say even more challenging, right?
Yeah.
Because they're going through from like something that's like in scope to not, whereas the random one, like you might have some, you know, a little bit of natural transfer.
Yeah, this one looks very challenging, but this one is already.
Well, because you're staying in that. I see. Are we supposed to read anything into the fact that in your last 2 partitions here, you didn't have a dev task, or is that?
Because we have 2 field tasks, so we didn't use that to select model checkpoint.
Okay, dev is just for selecting models. This is not like a outer loop mammal kind of choice thing, right?
Okay, so maybe to explain it a little more. Yeah, these are for model selection, and these trained dev are kind of for the mammal kind of inner outer loop. I hope that makes sense.
Dev is inner loop. Train is inner loop.
I think train is the inner loop, and you have a loss of that, and it back propagates to update your model.
And what do you do with tests?
Oh, tests, they are shown here, but they are. I actually forbid the model to access it during training. It just because sometimes the task appears here, sometimes it appears here, so I just reserve a test set.
Gotcha. So how does task ontology fit into this picture? Use that task ontology information in any way?
So just how we partition them, like using the categorization.
So for like 2.1 and 3.1, it's what goes in train and not is dictated by the ontology. Right.
I'm not sure I get the question. Oh.
I'm trying to answer, I guess, answer your question. Right, is it true that because you create the ontology that says these tasks are not classification tasks, and you want to study what happens if you train on non-classification and have the dev test the classification, so that allows you to do that.
Yeah, that's what our intention is.
And then how do you pick your model checkpoints for 3.1 and 4.1 so you don't have a dev?
We just train a fixed number of steps with some learning rate and type parameters that we feel in general working well.
Okay. Sounds good.
Cool. So let's continue. Okay, so here are 4 partitions. We actually have 8 in total in the paper. So if you're interested, please check the paper. And a little more on the experiment details. We mainly use a barge-based model for the purpose of our experiment. It's a encoder-decoder model with, I think, 100 million parameters, maybe. So we also verify some of our findings with larger or different model architecture. In general, we find the outcomes to be similar. And all of them are off-the-shelf transformer models pre-trained on large corpus with mask language modeling or very similar objectives. This is figures from the T5 paper. They mask some of the words and train a model to recover them. And the methods we compare, first is the straightforward one, and also our baseline is take the pre-trained model, directly fine-tune it. So for each task in t-test, the set of test tasks, you fine-tune it on train set, select best checkpoint on dev set, and report performance on test set. The standard way of doing fine-tuning. And the other methods we compare is we include this upstream learning phase shown earlier. We either implement it with multitask learning, which is we have the train task, we throw out the test sets because we don't want the model to see it, and we concatenate everything into a big training set. And train the model to do this multitasking on this set and fine-tune the resulting model on the unseen tasks. And also we try some meta-learning algorithms. I think some of the student or researcher here are interested.
For the multitask learning, for the first method, because you have different tasks, so you have different objectives, right? Yeah, how do you combine them? So you just stack all the data.
Yeah, first of all, we cast everything into the text-to-text format. So everything is a generation task right now.
Oh.
So we can concatenate them and train them together.
Sorry, you also have a regression task. So
that's also outputting a regression target. I know it's a non-standard way of doing regression, but to make it somehow uniform, we have to do this.
Is there a vocabulary issue with certain of the sets, like the sign language, where it's it's not something that would be the vocabulary of part-based?
Okay, that's something I didn't investigate. It might be possible, but we don't see any any result that are too bad that brings our attention. So
maybe it gets on, maybe it gets split into many small subwords, but whatever happens, you don't get a sync fault.
Yeah.
Okay, so you just use the default part vocabulary.
Yes.
Okay.
And some other methods we include in our comparison are some popular meta learning algorithms like mammal style or the first order variance. So due to the time limit, I'm not going to introduce them in detail. Okay, quick summary. We have our data, a set of diverse tasks, and partitioned into different trained depth tests. And our training recipe is have a pre-trained model, do upstream learning, and do downstream fine-tuning. So we have some very extensive experiments with these resources, and we summarize these key findings, and hopefully they can help people trying to build few-shot learners. First of all, our question is, can we teach a pre-trained language model to generalize across tasks with this upstream learning stage? Basically, we compare the model performance with or without it, and use this average relative gain metric we defined earlier. So evidence one, this metric we defined is positive for all of our 8 partitions and the 4 upstream learning methods. So in general, it's very helpful. And if we look at individual tasks, more than half of the tasks, they have more than 5% relative gain. And maybe 35% tasks, there's not much change. And maybe 12% of the tasks, they have negative transfer. But in general, it's trending towards positive. So we conclude that yes, upstream learning methods do help to acquire this cross-task generalization that we want.
So, sorry. So regular mammal is second order, right?
Yes.
And this is interesting because a lot of, well, so I can't remember, what is reptile? Is reptile different?
It just roll out more steps in the inner loop and does not do the gradient tape. It just use the final model, like subtract the initial point and use the difference as the gradient.
Okay. What's interesting is that, so there's a few cases, it's mostly that section 2 area, where the mammal cases, and not second order mammal, but first order mammal and reptile. And like first order mammal, I would think would be actually worse than mammal usually. This is better, are better, and then reptile is the best there. But in like the random case, which is that's you got the most training data, right?
Yep.
That's doing the worst relative to multitask training. We were just having this discussion about like how, man, mammal looks good. It always seems to help. I'm surprised more people don't use it more often. But this kind of is a counter to that conventional wisdom, or at least wisdom that we decided is conventional. I guess I wonder if you have any thoughts about that.
Yeah, we do. We find it also very surprising. So it's actually the second point here. We find that multitask learning is a strong baseline. It kind of outperforms meta learning algorithms in most settings. So we didn't investigate too much into this. Some of our hypotheses include maybe the mammal network is designed for simpler MLP networks. For transformers, it might be more complicated for it to optimize, especially second order optimization is involved. Or we just didn't tune the hyperparameters very well, but that's not the main focus of this study, so we decided not to pursue that task.
Usually meta learning has more, like you can see the added advantage of meta learning when you are really doing few-shot learning. So maybe if you did some more analysis or addition studies and few-shot or K-shot analysis, maybe be able to see where, like whether basically advantage of meta learning when you use less data for cross-task generalization or something like that.
So how many items did you have in your training sets for your tests?
16.
There's just 16?
Yeah.
That's pretty shot, right? And then, I mean, so Mojda, you also showed pretty nice gains with meta learning for MT fine tuning. Is this right? I can't remember the test. I thought it was it MT fine tuning?
It was on NER tasks.
Right, NER tests, right. And there, it was pretty consistent. Meta learning was helping, right?
Yeah, it was, in our case, in our evaluation setting, meta learning consistency helped. But because now what you are discussing is in compared to multitask, I'm thinking we basically didn't have an equivalent multitask evaluation because our setting was different. There's no such a, we cannot. Yes. So it's not the, like there were no direct comparison with the multitask setting as we have here.
Yeah. Right, we were doing, well, the different tasks were different languages. Right?
Yes.
That's also true. Right. Yeah. Anyway, so part of our story is out, but part of it has been suppressed by big NLPs.
Yeah, I would definitely love to learn more about how you use memo in your project and maybe get some inspiration. Some other findings include there are some negative transfer, and we find these tasks like resembles the pre-training objective well, and those tasks are more likely to get negative transfer. We also have the finding that like with different upstream learning methods identified by different colors here, the performance gain are quite correlated. Like if a task benefits from multitask learning, it's also likely to benefit from memo. And some more analysis. We have this, remember we have different partitions that's designed for this controlled experiments. So we fix our test tasks and control what our train tasks are. Like we control it to be either fully classification task or fully non-classification task or somewhere in between, identified by different colors here. And the results are actually also surprising because I would assume classification task helps classification task most, but it seems that in the end they have similar performance gain. So perhaps our understanding of task or the categorization of them may not align with how the model actually learn transferable skills.
So how do you evaluate generation tasks?
I'm sorry?
How do you evaluate the generation tasks?
Generation tasks.
Like
You mean
you have dialogue in there, I think, right?
Yeah.
So what's your evaluation method?
Use beam search to generate.
No. To score. How do you know how well you're doing?
You mean
Like accuracy or
Yeah.
Oh yeah, for generation tasks we use the metric that the task originally uses. Like it can be blue or root score.
Okay, so it's like a partial overlap kind of thing, right? And then classification tasks are generally like accuracy or possibly F measures. Right?
Yes.
And presumably when the classification tasks were originally actually classification tasks, they were constrained to classify in the space of the label set, but that's not true for you, right? So you actually have the capability, like I said before, you have the capability of generating, what kind of name entity is this case? And you say ice cream, right? And it's like not part of the set, or I guess ice cream could be a set. However, is the answer, right? So in those cases, presumably it's wrong.
Yes.
Did you by this probably? I'm guessing the answer is no, but I wanted to know: did you by any chance look and see about with the classification tests how often you would say the answer is like not responsive, like not even in the set of possible classes?
I look into some results that this is not happening. So
you're saying most of the time it is.
Yeah.
Like from a random selection, most of the time it's giving a valid answer.
Yes, okay. Or especially for classification tasks. Usually a few examples are enough to train it to constrain the output in that certain space. Okay.
Okay. Yeah. Right.
Okay, cool. I guess I'm a little bit slow, so I'm going to skip a few slides to make sure I have time to introduce some other stuff going on. So for this work called CrossFit, we designed a task setup and build dataset and resources to test this capability. And we find that upstream learning is in general helpful, but task similarity that we commonly believe, like classification versus QA, does not quite align with how models learn. So this sort of motivates our next project. So what's next? The past one is about acquiring and evaluating it. The next part will be how we can understand or better build a model that can explicitly model knowledge or skill sharing. So we want to bring up this previous work called routing networks. It's trained to multitask, but in each layer you can select what model parameters to use. And conceptually, these different model parameters correspond to different skills that are needed in solving that task. And I know there are other similar ideas happening in different areas. So our next project is built based on this. The topic is eliciting cross-site skills with task-level mixture of experts. This is the pre-frame and also accepted to findings according to the email I received this morning. We train a task-level mixture of experts model to multitask learn on the data we defined earlier. I'm going to explain more about what these models are. And we find they're better at few-shot learning on missing tasks. And we also find that the learned routes and experts, we can actually interpret some meaningful things from there. Cool. A little background of what mixture of experts are. This is a broad family of models. This is from lecture notes in a machine learning course. So basically, usually your input only goes into one fixed set of parameters to generate the output. But in this mixture of expert setting, your input first goes into a gating network identified by this HX here. It outputs probabilities of P1, P2, P3, corresponding to how much you should rely on expert 1, expert 2, and expert 3. So your final output will be the weighted average of these output Y1, Y2, and Y3. So this is a basic background about mixture of expert models. And there are many variants based on this concept. You can route different tokens in your sentence into different experts, or you can route different instance input-output pairs to different model parameters, or you can route different tabs to different experts. So all of these are explored before, and people find this to be useful. And in this work, we want to focus on task level mixture of experts models because we want to interpret how these skills and knowledge sharing happens within the multitask model we train. So this seems like a good fit. And these are some prior work that have been doing this, but probably in a different setting. The routing network is doing MNIST digit recognition, and some are done for machine translation, and some are done for like different set of tasks. But this is like appearing in a blog, so probably many details are not known to us. So the experiment setup on the left-hand side is the data that we introduced in the first half. We still use the same data the random partition in particular, but we exclude two tasks because they seem to have large variance in our experiments, so we just decide to discard them. On the right-hand side is our mixture of expert version of transformer models. So basically, these would be the transformer layers you see normally. We duplicate them for 3 times, and just in each layer, train a gating function or router to select which one to use. So similar to previous project, we use BART-based as our testbed. And yeah, so far it seems like we have the data and we have the model. This problem should be solved, right? But it's not really the case until we really look into it. Like the reality is so hard. I want to point out why this is difficult. So there is this router network that you need to learn. If it learns to select or favor one expert in particular, it just degenerates to the non-mixture of expert case. That's not what we want. And or maybe it learns to output the same weight for every expert. And then we still cannot benefit from this mixture of expert design because it's not actively selecting anything. So it's very easy for this model to degenerate to something that we don't want. So that makes us to start a wild exploration of how to make it work. But these are like very low-level details, so I'm going to go through them very quickly. First of all is what selection function to use. We compare normal softmax with 2 other variants called gumbo softmax and gumbo softmax with straight-through estimator. Basically, they add noise and they help you to make your selection more discrete. And by comparing these 3, we find that the last one works better, but it's still sensitive to temperature, and like there's a temperature parameter in your softmax. It's very sensitive to how you set that. And a few more important factors include how you decide, how you formulate your batch, where we find like mixing different tasks into a same batch is more helpful than not. And the third thing we find useful is to set different learning rates for your router and your transformer expert parameters. You probably need smaller learning rate for your transformer parameters, but larger learning rate for your router. And also you need a very low level detail. You need to pay attention to how you clip your gradients. And the last thing we find useful is to adopt a 2-stage training recipe. Basically, in the first stage, you train normally. In the second stage, you freeze your router and reinitialize your pre-trained weights. We find this to be useful to be not forgetting anything from pre-training, and also not to in the beginning of your training, your router might not be learned well, so that might cause you to learn some unuseful thing in the expert. And this is our way to recover that. So yeah, these are the 4 aspects that we find to be useful in our training. And some other less important factors that we try, but we don't find them to be useful, so we just choose some default selection. One more thing I want to point out is that there's some discrepancy between the train loss, depth loss, and the final performance. So the solid lines, they are the loss throughout the training process. You will see these are the datasets, I think. So it will decrease and then gradually increase, suggesting that it might overfit at this point. But if you look at the final metric and aggregate them, these are the dashed lines on the upper side. You will see they still continue to grow after you train it for so many steps. So that's a lesson we learned from our experiments. Probably we should not select your model based on your depth loss. Sometimes your loss term does not like perfectly resembles your final performance. So if you care more about performance, you should always select your model based on your performance. Okay, so how well does the model perform? As I mentioned earlier, we trained this model to multitask on 120 tasks. This is tested on these exact same tasks to kind of see how the model learns on these in-domain tasks. We report the average of performance on a development set. So this is the BART base performance. And we have several baselines, like we have 3 experts to choose from. These baselines are basically randomly choosing 1 out of 3, choosing 2 out of 3, or choosing all of them and taking the average. So this is where the first interesting observation comes in. If you introduce sparsity or the experts naively by randomly selecting 1 out of 3, this will actually hurt the performance. But surprisingly, if you choose 2 out of 3 experts, this will improve the performance. And if you compare this 2 out of 3 with the BART-based or average model, so these 2 all the weights are completely shared across different tasks. But for this 2 out of 3, some parts are shared, some parts are not. So this kind of suggests that sharing all the weights may limit your performance, because different tasks require different skills, and if you force them to use all the same weights, the model might be limited.
Sorry, just to make sure I understand. The idea here is you have 3 experts, right?
Yeah.
And then in all cases, you still use the separate parameters to learn how much to trust each expert when making your decision, right?
Can you repeat that?
The mixture of experts thing, you're always using all 3 experts with some relative ratio, although if you use the pass-through number, that gives you a hard choice ultimately, right?
Yeah, but if that gives you a hard choice, then effectively some experts are not used.
Yeah. Right. So, and then what you're just saying is like, in the first case, each expert gets different tasks. Is that what you're saying? Right. In the second case, there's overlap between experts.
The first case is there are still some overlap because you have more than 3 tasks. Some of tasks are randomly selected.
Well, right. So the tasks are always the quote unquote tasks are actually just a mix of things from a bunch of tasks, right? Because you said you did heterogeneous tasks.
Oh yeah, yes.
So each task is actually all tasks. It's just like a subset of data.
Yeah, like each instance is relative to different.
And but it's just partitioned into like expert 1 gets this, expert 2 gets this, expert 3 gets this.
Yes.
And then in case 2, there's like a partial overlap. So like task A goes to experts 1 and 2, task B goes to experts 2 and 3. And then in the third case, you're just training 3 experts, but they all get all the data.
Yes.
Got it. Okay, good.
Cool. Yeah. To continue this bar chart, our task level measure of expert model can match the performance of the task random 2 out of 3, which is the best baseline. But meanwhile, it has it uses less computation at inference time, because in these, when we apply the Gumbel softmax thing, they usually output very discrete selection at the end. So they only use 1 out of 3, but this one uses 2 out of 3, which doubles the computation cost. So in this case, we think task level mixture of experts are still very useful.
Sorry, question.
Yeah.
At what level do you combine these experts? Do you combine it at So do you combine it at the very last layer before making the prediction, or are these experts tightly integrated? Are these 3 separate models?
Oh, so transformer model has maybe 12 layers. At each layer, we select 1 out of 3 and aggregate, and then next layer we select again.
And it's a new selection for every generated work.
And not the work, just the task. Like every task route is different.
Okay, and so every instance of task.
Yeah. if there are two instances in the same task, our model kind of restrict them to be routed in the same path.
Rather than same task. Okay. And that wait. What's the information you use to do the decision? Because you have multiple instances for like there's a whole test set for every task, right?
Yeah.
So is it like you give it like all 16 of the I don't know how many instances you put in the test set?
The test set has more than 16 examples.
Whatever. So every of the 100 examples, you put in all of the contexts in order to make the decision about which expert you route through?
Maybe we can go back a little bit. So maybe in this figure, this router only takes in task representation as the input.
That's representation.
Yeah, that's not detail that I discarded. But basically, if you have 120 tasks, one easy way of implementing it is 120 embedding.
Okay.
So you're assuming that you know the task ahead.
I'm sorry?
So you're assuming that you know the task ahead of time, such that you're.
Yeah, you know what task you're dealing with.
Okay, how do you get the embedding? It's not just the numbers 1 through 120, right?
Yeah. So during multitask learning, this is trained all together.
Okay. Got it. I see. Okay, so the code goes in.
So in this figure, what's the efficiency argument you made? So if you stop when we use the softmax, it's usually a peak. So you get a peak, usually one out of the expert. But my question is, to compute the softmax, don't you have to have all this pre-computed? Then.
Oh yeah, you have to compute this absolutely for everything, but for these, you don't have to compute every expert.
Okay. So in 2 out of 3 cases, you randomly picked 2 of those experts, whereas in softmax, it usually converts to 1.
Yes.
And which is not random, it's because of softmax, which is a learned pick.
Yes. Cool. I'll try to be fast. Is the time limit very strict, or is it okay? Thank you so much.
What's the difference between MOE 1 and MOE 2?
Okay, so sorry. So I highlighted 2 things here. Whether it's a randomly initialized embedding or it's some pre-computed task embedding from some prior work. So the 2 means whether you're using random or the second one. I should have put that in. Okay. So we were talking about multitask learning, but we are also interested in how we can adapt this model to new tasks and see if it can do it quickly. So this would be the performance of doing generalization to unseen tasks. And we report the average relative performance gain metric we introduced earlier. And to do this, we use the pre-computed task embedding setting, because that's how we connect this seen task to unseen tasks. So that's also why we train task MOE1 and task MOE2. This is the 2 which adopts this pre-computed task representation, so we can reuse the router to predict the routes and test the performance.
How does that compare to the results that you got on multitask learning and mammal?
So this blue chart is actually multitask learning. We didn't test mammal because in the previous work, we find this to be more effective.
But this is with all the training tests, so 120.
Yes.
120.
Cool. Do you know where MOE1 would go in this?
I think in that case, the roles for unseen tasks, we have no knowledge of what they are going to be. You can either train the whole model, but I'm not sure if your model can figure out the right routes with 16 examples. That's something I haven't tried, but yeah, that's a good point. Okay. Cool. Let me try to.
What's the input to the off-the-shelf?
What do you mean?
To get an embedding the task from the off-the-shelf model, what goes in?
The few-shot example, the input of the few-shot examples.
No. It's just like a sentence embedding?
I similar, but they use something called Fisher information that involves some gradients. But only the few-shot train set is used to make sure we don't violate the few-shot setting. I'm going to wrap up quickly. Cool. And this is a more detailed breakdown of all the unseen tasks and how their performance improved or not improved after this upstream learning. And our task level MOE model is in orange here. We kind of see it avoids negative transfer because the bars are smaller, and overall it gets a higher performance in the end. Cool. And what more can we learn from this model is we look into the routes that it learned and look into the learning dynamics of how they formulate. So this is a dynamic graph of how they're learned. So take a snapshot of it. In the very beginning, when your model is trained for 3,000 steps, we can already observe some patterns that are developed here, like these marked in orange are classification tasks, or green are generation tasks, other tasks, and QA task. You will see that classification tasks have a very visible pattern here, and generation task has a visible pattern. Other task has a visible pattern here. So this is using randomly initialized task representations, meaning the model has no prior knowledge of these categories we define, but they do get to discover these patterns from training the routers.
Well, when you have two, like, if there's like a thick bar, that means it's like choosing two experts, right? A thick dark bar, like in that early set of tasks, like layer 4 and layer 5. Okay,
so this is separation of 4 and 5. It's maybe the last expert in layer 4 and first in layer 5.
So my dark was pretty much decided.
So, and gradually it learns more fine-grained and more discrete decisions. And in the end, this is what you get.
Yeah. What did he use to create this? He just left off there.
Yes.
Nice.
And one last analysis we did is we try to see how the learned routes correlates with our understanding of tasks. So we define several hand features, like, is this task extractive? Does it require word knowledge? Does it have short input? We have a table like this for several features in every task. We have this table of expert selection and task. And so we can compute a correlation between the features and experts. This helps us to understand, but it by no means completely explains how your model transfers knowledge and skills. It just helps us to understand. So this would be the heat map of the correlations we find. So these are the encoder experts, decoder experts, and some pen features that we select, like, is it classification? Is it extractive, long input, short input? And we do have some strong correlations appearing. Like, these highlighted colors are all having very strong significance. And you can see that maybe one makes very good correlation. So conditional generation is perhaps heavily dependent on this expert 2 in layer 9. And maybe this QA task is very dependent on expert 2 in layer 3. These are verified with some expert disabling experiments. Like, we take out this expert and ask the model to do inference, and we find the performance drop a lot. So that's how we find out, like, they are indeed doing something for that specific category of tasks. Cool. Yeah. Conclusion. So we explored adapting transformer models to a mixture of expert model and training this model on diverse NLP tasks. And we find that there are a lot of design choices and they matter a lot to the final training procedure. The final model is better at few-shot learning on the instinct task, and the learned routes and experts partly align with our categories of tasks through our heat map and the dynamics and what we interpret from them. So that's pretty much the conclusion and pretty much for my talk. I have one last slide summarizing the work, and huge thanks to my co-authors. That's the end. Thank you. Yeah, happy to discuss any questions.
Thank you, Qinyuan, for the great talk. Since we are short on time, maybe we will just accept one question if there are like any really like burning questions that the audience have. Otherwise, we can also anyone who wants like to reach out to Qinyuan can do that offline too. Okay, so yeah, thank you so much for joining us for this annual seminar. Can you stop recording?